we have now a good understanding of electric potential. We're going to tie that back to electric field strength and have a look at how those two things are related. You'll notice here we've used the term potential gradient. Just want to draw your attention to the fact that gradient now has two different meanings. So far, the one that you will have seen and the one that you are familiar with is the slope of a graph. So that's one use of the term gradient. Another use of the term is a change over distance. So if we're looking, in this case, potential gradient, we're looking at the change in potential over a distance. I want to just make a little comparison here with if we're looking at a rate. A rate would be a change over time. So for example, if you talk about velocity, that's a rate of change of speed. So a rate deals with a change over time. A gradient deals with the change over distance. So just something to keep in the back of your mind as we look through some of these concepts. And just to be aware that the different use of the term gradient, whether it's to do with a graph or to do with a change over distance. Okay, linking back to Unit 5, and we also mentioned it briefly earlier in Unit 10 as well. I want to just remind you that electric field strength, what we interpret that to mean, and we consider it to be electric field strength at a point is the force per unit charge. And that means that we can calculate the electric field strength using the equation E is equal to F over Q. And if that's the calculation that we would do, then the units would be newtons per coulomb. So force being measured in newtons, charge being measured in coulombs, and we end up with the units for electric field strength of being newtons per coulomb. Just a little side note here, we'll come back to this a bit later, but we could rearrange that to indicate that the force that would be required to move a charge through an electric field can be calculated just by manipulating that equation to give F equals QE. So just recall that, keep that in the back of your mind. We're going to continue now looking at a uniform field, and we'll relate the uniform field electric field strength to potential gradient. So if we deal with this scenario here, where we've got positive charges on this side and negative charges on this side, what we would see is a uniform field in between the plates. Again, there are the edge effects that start to occur outside the edge of the plate, but we're not interested in that. We're only looking at the uniform field inside. Now, important to note here that these plates are separated by some distance d. And if we consider again that idea of looking at a charge, if we had, say, a positive charge here, we would apply a force to it that would cause it to move to the left, and that force, as we saw above, would be equal to, it should actually indicate that these are vectors, would be equal to the charge multiplied by the electric field strength. Now, if we move that charge, just note that that's charge Q. So moving charge Q against the field E requires work. And we've seen in the past, and I'll just reiterate it here, the work that would be done in that case is equal to the charge multiplied by the potential that it's moving through. And that potential in this case is supplied by the source down the bottom, or the EMF down the bottom. However, work can be defined in another way. So work is also defined as the product of the force required to move an object through a distance. Now we'll see that in a bit more detail in the Unit 2 mechanics, but just to tie it in here very briefly. So the expression that we would use there is that work is equal to force times distance. I'm using the distance as a d here. You might see it as an s in other sources, but we'll use d to tie into this diagram that we're dealing with. So we have that equation, but you'll notice now we've got these two expressions for work in this scenario. So we can equate those two and say that QV is equal to F times D. So the work done in moving the charge through that field is Q times the potential, but it's also equal to the force multiplied by the distance through which the charge is being moved. And you will recall, we just saw above, that that force can be expressed as Q times E. So just putting in brackets to highlight that, the force here is Q times E. Notice we've now got Q on both sides, so we can cancel the Q's, and we're left with V is equal to ED. Or, more specifically, if we rearrange that, we can say that the electric field strength is then the potential divided by the distance between the plates. Or in other words, the electric field strength is the same as the potential gradient. Just make a brief note here as well. If we're looking at the units here, potential is measured in volts, distance is in meters, so electric field strength now has two appropriate units. We could use newtons per coulomb, or we could use volts per meter. So we can then figure out what the magnitude of the electric field strength is if we know the potential difference and the separation of the plates in this scenario.